Hello class, today's lecture is about the application of Newton's laws of motion. So we learned Newton's laws of motion in our previous chapter. There is 3 laws basically. Now let's learn their applications. So these are the learning objectives for this chapter. You will learn about frictional forces, springs, translational equilibrium and circular motion briefly. And this is the chapter outline. Newton's laws of motion can be applied to a variety of systems. So this chapter shows how Newton's laws are applied to friction, springs, connected objects and circular motion. Now let's discuss each of these sections separately. So in chapter 5, we assume that surfaces are smooth and that objects slide without resistance to their motion. However, no surface is perfectly smooth. When viewed on the atomic level, even the smoothest surface is actually rough and jagged as indicated in this figure. So to slide one such surface across another requires a force large enough to overcome the resistance of these microscopic hills and valleys bumping together. So this is the origin of the force we call friction. Therefore, friction is a force exerted between the surfaces in contact and it has its basis in surfaces that are not completely smooth. Now let's see some day-to-day examples of frictional forces. Suppose for example that you are standing still and then decide to begin walking forward. The force that accelerates you is the force of friction between your shoes and the ground. And we simply couldn't walk or run without friction. It's hard enough when friction is merely reduced as on an icy sidewalk. Similarly, starting and stopping a car and even turning a corner all require friction. Examples of systems with small and large amounts of friction are shown in this figure. So sometimes it is desirable to reduce friction and in other case we want as much as friction possible. So for example, it's more fun to ride on a water slide if the friction is low, but however when running we need friction to help us speed up, slow down and make turns. The sole of this running shoe, like a car tire, is designed to maximize its friction. Now there are two most common types of friction, kinetic friction and static friction. Kinetic friction is the friction produced when surfaces slide against one another. First, imagine attaching a spring scale to a rough object like a brick and pulling it across a table as shown in this figure. If the brick moves with a constant velocity, then Newton's second law tells us that the net force on the brick must be 0 since the acceleration is 0. Therefore, the force indicated on the scale F has the same magnitude as the force of kinetic friction, which we called as Fk. K represents kinetic and F is friction. Now, if we repeat this experiment, but this time put a second brick on top of the first, we find that the force needed to pull the brick with constant velocity is doubled to 2F. So we need more force. So from this experiment we see that when we double the normal force, for example by stacking 2 bricks, the force of kinetic friction also doubled to F. So this force that opposes the motion we call as kinetic friction. So in general, the magnitude of the force of kinetic friction is proportional to the magnitude of the normal force N. This is stated mathematically as Fk equals mu k times n. Mu k is the proportionality constant and n is the normal force, Fk is the kinetic friction. So in here mu k is called as the coefficient of kinetic friction. Now Fk and n, the kinetic friction and normal force, are both forces and therefore they have the same units of force, which is Newton. And according to the definition of kinetic friction, the direction of kinetic friction should be opposite to the direction of motion. And the coefficient of kinetic friction mu k is a dimensionless number and it is always positive, ranging between 0 and 1 values. And when mu k is greater, then the friction Fk is also greater. And the kinetic friction is independent of the relative speed of the surfaces and independent of the area of contact between the surfaces. Now let's see an example that consider a commonly encountered situation. Someone at the other end of the table asks you to pass the salt and you slide the 50-gram salt shaker in that direction, giving it an initial speed of 1.15 meters per second. Now if the shaker comes to rest with constant acceleration in 0.840 meters, we are asked to find the coefficient of kinetic friction, that is mu k, between the shaker and the table, and how much time is required for the shaker to come to rest if you slide it with an initial speed of 1.32 meters per second. Now let's picture the problem first. At first, the shaker is on the table, then it slides with a speed of 1.15 meters per second. Now we choose the positive x direction to be the direction of motion and positive y direction to be upward. Now there are two forces acts in y direction. The shaker's weight, which is W, which is equal to mg in y direction, but it is in negative y direction, because of that it is a negative value. And the next one is the normal force N, and it is in the positive y direction. Now there's only one force acts in the x direction, the force of kinetic friction Fk, the friction force that opposed to the direction of motion. Therefore it is negative because it is in the direction of negative x direction. Now we can draw the free body diagram with these three forces. W, the weight, is in downward direction, normal force in upward direction, and the friction force, kinetic friction, is in the negative x direction. Now these are the known parameters. We are given the mass of the salt shaker, initial speed, and the sliding distance. And we are asked to find the coefficient of kinetic friction. So the coefficient is mu k and the time to come to rest, which is t. So to find mu k, we need to find Fk. We know the equation with k equals mu k n. So now let's apply Newton's second law in x direction. Since there's only one force in x direction, which is the friction force Fk. So we can apply Newton's second law of motion in x direction, which is sigma Fx equals mass time acceleration Ax. Now the force in x direction is negative Fk because it opposes the direction of motion. Therefore we can write Fk equals negative mass times acceleration. Now we need to find the acceleration. In order to find Fk, we need to find Ax, acceleration in x direction. So for that we can use kinematic equations, because we know the initial velocity and we know the final velocity. Because it comes to rest, it should be 0, and we know the sliding distance delta x. Therefore we can use the kinematic equation Vx square equals V naught x square plus 2a delta x. And from this equation we need to find the acceleration. Therefore let's isolate acceleration first. Equals 2ax delta x. Now we can isolate the acceleration. Ax equal bx square minus v naught x square over 2 times delta x. So we know all these parameters, we can substitute the values. The final velocity is 0 because it comes to rest at the end. Initial velocity is 1.15 meters per second. It is given, and the the delta x sliding distance is given. It is 0.840 meters. Now we can find the acceleration. It will be a negative value, 0.787 meters per second square. That is the acceleration in x direction. Now we need to find the normal force. So we know the acceleration and we know the mass, so we can find the friction force. But for that we need to find the coefficient of kinetic friction, we need the normal force. The normal force is in the y direction. Therefore, we can apply Newton's second law in y direction. In y direction, we can apply Newton's second law. That means sigma Fy equals mass times acceleration in y direction. Now, we know that the salt shaker is moving in x direction. Therefore, acceleration in y direction is 0. And what are the forces in y direction? It has normal force and it has the weight, but weight is in downward direction, therefore it is negative. This is equal to 0 and n is equal to W. We know W is mass times gravity, mg. Now we know all the terms, so we can find the coefficient of kinetic friction. So it is Fk equals mu k times n. Therefore coefficient of kinetic friction mu k is kinetic friction over normal force, and kinetic friction, we found it here, it is mass times acceleration. So it is negative mass times acceleration, and normal force is mass times gravity. So mass get cancels, it is negative acceleration over gravity. Therefore we can substitute the values, and we found acceleration, it is negative 0.787 meters per second square, and gravity value is 9.81 meters per second square. Therefore, the coefficient of kinetic friction is 0.0802, and the units get cancels and there are no units because it's a constant. There are no units for the value. Now in part B, we are asked to find the time for the salt shaker to come to rest. So we simply can use the kinematic equation to find time. Now we know the final velocity, which is 0, and initial velocity, and also we know the acceleration. Therefore for part B, we can use the equation Vx equals V naught x plus Ax t. So now we have to find t. So let's isolate t from this equation. Vx minus V naught x is equal to acceleration times t. Therefore t is Vx minus V naught x over acceleration. So we just have to substitute the numerical values. Final velocity is 0 and initial velocity is given 1.15 meters per second. Acceleration we calculated is 0.787 meters per second square. The negative values get cancelled. The answer is 1.68 seconds. So in this problem we calculate the coefficient of kinetic friction involving Newton's second law of motion and the kinetic equations that we learned in our previous chapters. Now let's see one more example, but this time with an inclined surface. Let's read the problem with the picture. A trained sea lion slides from rest with a constant acceleration down a 3-meter long ramp. The length of this ramp is 3 meters into the pool of water. If the ramp is inclined at an angle of theta, this angle is theta, which is 23 degrees above the horizontal, and we are giving the coefficient of kinetic friction mu k between the C line and the ram. The value is 0.26, and we are asked to find the time it takes for the C line to make a splash in the pool. Now we first have to choose the axes. So in inclined surface, we choose one axis to be parallel to the surface, and then the other axis should be perpendicular to it. Therefore, the C line accelerated in positive x direction. Therefore, the acceleration in x direction is greater than 0. It has a positive value, and it started from rest. Because of that, initial velocity is 0. Now we can choose the initial position of the C line to be at x naught equals 0 at the origin, and there is no motion in the y direction. It's sliding in the inclined surface which is in x direction. Therefore, the acceleration in y direction should be 0. Now the next step is to draw the free body diagram to find the forces acting on the C line. So this is the free body diagram. The normal force is always perpendicular to the surface, and the weight is always vertically downward, and the angle is theta. Therefore, we can find the x and y component of weight. Y component is W cosine theta. W is equals to mg, and it is mg cos theta, and x component is mg sin theta or W sin theta. Now from the free body diagram, we know the normal force in positive y direction. Because of that, it is ny hat, and the kinetic friction is in the negative x direction. It's always in the opposite direction of the motion. Therefore, it is a negative value, mu k times normal force times x hat, the direction. And then the weight is always in downward direction, and if we find the x and y component, we can write W in terms of x and y component. X component is mg sin theta, and it's in the positive x direction. Y component is mg cos theta, but it is in the negative y direction. Now we are asked to find the time. For that, we can use kinematic equation, which is x equal x naught plus v naught t plus half at square. Now for that, we first have to determine the acceleration in the x direction. For that, we know that we can use the Newton's second law of motion in x direction, which is F equals ma. And now to find the force in x direction, we have to find the frictional force Fk, and we know that Fk is mu k times a, and mu k is given. We can find the normal force. So normal force we can find by using Newton's second law of motion in y direction, because the y direction, the acceleration is 0. Now can you do the calculations by yourself? Try to do the calculation by yourself and then check the next slide. Now these are the known parameter, length of the ram, and the theta, angle of incline, and the coefficient of kinetic friction. And we are asked to find the sliding time t. First, let's find the x and y components of force vectors. The first step is to find the x and y component of all the vectors. So normal force is always perpendicular to the surface, and it is in the y direction. Therefore, x component is 0 and y component is just the normal force n. And for friction force, we saw that it is in the negative x direction. Therefore, it is negative Fk, or we can write Fk is mu k times n. Since it is directed in the negative x direction, the y component is 0. And for weight, we saw that weight has both x and y component, and y component was mg sin theta, x component was mg sin theta, y component was mg cos theta, but it was directed in negative y direction. Therefore, it's a negative value. Now the first step was to find the normal force n. We said that to find the normal force, we can apply the Newton's second law of motion in y direction, which is sigma Fy equals MAy. It is 0. There is no motion in the y direction. And the force in y direction was, these are the forces in y direction: Ny, Fy, Fky and Wy. Fky is 0, therefore it is n minus mg cos theta is 0. Therefore we can write normal force is equal to mg cos theta. So now we found the normal force. Next, to find the acceleration in x direction, we have to use the Newton's second law of motion in x direction, that is F equals ma in x direction. Now the x direction forces are, nx is 0, we have the frictional force and the weight, the component of weight in x direction. So which is mg sin theta, and the friction force is Fk. This is equal to mass times Ax. And we know that Fk, what is the kinetic friction? It is mu k times n. Normal force is, we found normal force here, mg cosine theta. So we can write mg cos theta equals mass times Ax. Therefore from all these terms mass get cancels. And we can find acceleration Ax is equal g sin theta minus mu k g cos theta. So we can isolate g from here, and it is sin theta minus mu k cos theta. Now we know all these values. We know the inclined angle theta, and we know the coefficient of kinetic friction and the gravity. So we can substitute the numerical values and find the answer. G is 9.81 meters per second square, and sin theta is 23 degree. Mu k is 0.26, and cosine theta, cosine 23 degrees. Therefore the acceleration is 1.5 meters per second square. Now we found the acceleration. So we just have to find the time. For that, as we said earlier, we can use the kinetic equations: x equal x naught plus v naught t plus half a t square. And here initial position is 0 and the initial velocity is 0. Therefore the equations become half ax t square. Now we have to find t. We can isolate t here. T square is 2x over ax. Therefore t is square root of 2 times x over ax. Now we know the values of x. X is given, it is 3.0 meters, and the acceleration we calculated 1.5 meters per second square. Now solving this, we get the time, sliding time, as 2 zeros. Now it is useful to compare the sliding salt shaker in our previous example with this sliding sea lion in this example. So in the case of salt shaker, friction is the only force acting along the direction of motion, which is opposite to the direction of motion, and it brings the object to rest. So we saw that in our previous example. Now in this example, because of the slope, the sea lion experienced both of a component of its weight in the forward direction and the frictional force opposite to the motion. Because it's a inclined surface, the friction force is in the opposite direction of motion, and we have the forward, in the forward direction we have a component of W, which is W sin theta. Now because this component of the weight W sin theta is the larger of the two forces, the sea lion accelerates down the slope, and friction only acts to slow it progress in this case. Now, as I said earlier, there is another type of friction which is called static friction. So, static friction tends to keep two surfaces from moving relative to one another. Like kinetic friction, it is due to the microscopic irregularities of surfaces that are in contact. The force generated by this friction acts to oppose the sliding, which is called static friction, or in symbolic form we can write Fs. Here S means static, F is friction. So let us start with a brick at rest on a table with no horizontal forces pulling it. So in this case, the force of static friction is 0. So no forces is needed to keep the brick from sliding. Next, we attach a spring scale to the brick and pull with a small force of magnitude F1. A force is small enough that the brick doesn't move, let's say. Now, since the brick is still at rest, it follows that the force of static friction, which is Fs, is equal to the magnitude to the applied force F1, but it is not moving. Now we increase the applied force to F2 to a new value which is still small enough that the brick stays at rest. In this case, the force of kinetic friction the force of static friction is equal to F2. So it is increased, but it is still at rest. So if we continue increasing the applied force, then we eventually reach a value beyond which the brick starts to move, and then the kinetic friction takes over. We know that kinetic friction happens when something is in motion. So when we increase this applied force, so the value reach beyond a value which the brick starts to move, and therefore the kinetic friction takes over. Now it follows that there is maximum force for the static friction, which is Fx max, that can be exerted by static friction. Therefore the force of static friction Fs can have any value between 0 and the maximum value, and after the maximum value the kinetic friction takes place. Therefore the static friction Fs can have any value between 0 and the maximum Fs, and the maximum force is proportional to the magnitude of the normal force. And then if we find the equation, it is Fs max is equal to mu s times n, and this mu s is the coefficient of static friction. It is s not k. Now like kinetic friction, static friction also independent of the area of contact, and it is parallel to the surface of contact and in the direction that opposes relative motion, like in kinetic friction. So let's see a quick example in static friction. A flatbed truck slowly tilts its bed upward to dispose a 95 kilogram crate. For small angles of tilt, the crate stays put, but when the tilt angle exceeds theta equals 23.3 degrees, the crate begins to slide. So now we are asked to find the coefficient of static friction between the bed of the truck and the crate. Now first we align our coordinate system with the incline. So x direction is in this direction and y direction is positive, and it is perpendicular to the surface. Now there are three forces acts on the crate: normal force, weight, and the static friction. So the normal force is always perpendicular to the surface, therefore in an inclined surface it is in the positive y direction, and then the static friction force Fs is always opposed to the direction of motion, therefore it is in negative direction, and the kinetic friction coefficient is, the static friction coefficient is mu s. And the next force is the weight, which is always in downward direction, and as usual it has x and y component both. X component is mg cos theta, mg sin theta, and y component is mg cosine theta, and both are y direction is, it should be negative. This should be negative. Now we can draw the free body diagram including these three forces. We have the normal force perpendicular to the surface and weight always vertically downward, and the frictional force is opposed to the motion, that is in the negative x direction. Now these are the unknown known parameters: mass of the crate and the critical tilt angle, which is 23.2 degrees, and we are asked to find the coefficient of static friction, which is mu s. So when the crate is on the verge of slipping but has not yet slipped, its acceleration should be 0 in both x and y directions. So on the verge of slipping means that the magnitude of the static friction is at its maximum value. So it is at fx max. Therefore we can set the y direction acceleration is 0. Therefore if we apply Newton's second law in y direction, F equals ma(y), and it is 0. So from that we can find the normal force, and then we can use the Newton's second law in x direction, and it is again at 0 on the verge of slipping. From that we can find mu s, the coefficient of static friction. Now as usual, first let's find the x and y component of force vectors. For normal force we saw that it is x direction it is 0 and y direction it is just the n. So if you remember, we have the weight in downward direction and this angle is theta, therefore this angle is theta, and now we have the static friction force opposite to the x direction, and then we have the normal force perpendicular to the surface. This is x direction and this is y direction. Now for the frictional force, it is in the x direction but it is in the negative x direction, therefore it's negative fx max equals mu s n, and the y direction, the static friction is 0 because it's only in the x direction opposite to the direction of motion. But for weight we have the both x and y components. So the x component is w sin theta, w is equal to mg, therefore it is mg sin theta, and then y component is w cosine theta, and w is mg, therefore it is mg cosine theta, but it is negative because it's in the negative y direction. Now to find the normal force, as we discussed earlier, we can use Newton's second law in y direction. So it is sigma Fy equals ma(y), and y direction there is no motion and therefore it is 0. Now what are the y components of forces in y direction? We have Ny, which is n, and the friction force is 0, and we have Wy. We just have Ny plus Wy equals to mass times Ay, or it is 0, and Ny is simply n, and Wy is mg cos theta, which is equal to 0, and therefore normal force is simply mg cos theta. And next, to find the coefficient of static friction, we can use the acceleration in x direction. It is again 0 because it is on the verge of slipping. Therefore in the x direction we can use Newton's second law of motion. Again it is equal to 0. Now what are the forces in x direction? We have normal force, it is 0. We have the static friction Fsx, and next we have the component of weight in x direction 0, and Fsk is minus mu Sn because it is in the opposite direction of motion, and x component is mg sin theta. which is equal to 0. Therefore, we can write mu s n equals mg sin theta. Now mu s n is again mg equals mg sin theta. Mu s is not mg actually. We found that normal force is mg cos theta. Therefore, mu s is mg sin theta over n, and it is mg sin theta, n is equal to mg cos theta. Therefore, it is equal to tan theta. Mg and g get cancels out. And now we know the angle. It is 23.2 degrees, and if we solve for the value, we get 0.429. That is the coefficient of static friction. Now you know how to find the coefficient of kinetic friction and coefficient of static friction, and thereby you can find the kinetic friction and static friction. So that's the end of the section 1 in our chapter 6.